In this video, we're going to continue just thinking about what functions are, but specifically how we can combine functions or maybe how we can build functions from existing functions. So first, just to think about, we can combine functions algebraically. That means we could add or subtract, multiply or divide functions together. Basically, you just want to think of what you start with and think of their individual domains. And as you combine things, keep those original domains kind of in the back of your mind. So let's run through an example quickly. Let's say we're looking at something involving division. So if I told you f of x was x squared, g of x is the square root of x minus 1, and I want you to divide function f by function g, it might be helpful to begin by thinking about the domains and ranges of both of the original ones. So for x squared, domain is all reals. The range is just from 0 to infinity. For the square root function, the domain is going to be from 1 to infinity because that square root idea has shifted 1 to the right, and the range is from 0 to infinity. For what we're looking at here, function f divided by function g, it's simply this. Now there are times where we could continue to simplify this a bit. In this particular case, I really can't, so I'm kind of done. But I do want us to think about what the domain of this new function is. In the numerator, really have no issues. That chunk could be anything. But in the denominator, we still have that square root idea. And so it's going to be related to the 1 to infinity here. The only difference I need to make is that I'm not going to include 1 as the domain. If I actually plug a 1 in here, 1 minus 1 is 0, square root of 0 is still 0, and then I end up dividing by 0. That's bad. So my domain is just going to be from 1 to infinity, but not including the 1. For times where you can simplify, just remember you always have to go back and look at the original statement before you simplified. So you'd always start by looking at this piece, and if you could simplify, that's great, but this is where you look to find the domain. And again, you can add or subtract or multiply functions as well. Okay, we can also think of building functions through composites. That's where you take an x value, you're going to plug it into function g and get an answer. You take that answer, plug it into another function, maybe function f, and you end up with a final result. So there's kind of two ways that we can describe that. We can describe that change as f of g of x with a lot of parentheses here, or this is another type of notation, f of g of x as well, but we just use this little circle in between. But the key idea is that we want to be able just to plug in an x and go right to that final answer, not have this middle step in between. So we want to think about how we can combine function g and function f together to kind of make sense of that. The other thing I want to point out in this picture is that we plug it into g first and then into f. In our notation, g is actually kind of the second thing that we see, but we start from the inside, so we're going to plug something into g first and then we would plug something into f, or plug that answer into f. So let's look at an examples that will probably make things a little bit more clearer. Again, let's look at the same functions we had before, same domains and ranges for those functions. But if I said find f of g of x, it means take function g, take this square root idea, and plug it in to the x of function f. Okay, so that's going to look something like this. Instead of just saying square x, I'm going to be squaring this function. And when I square this function, the squared and the square root kind of cancel each other out. So really this is what the function will look like. It's just going to be a line. However, when I think of finding the domain of this function, and to a certain degree the range as well, I need to think about this unsimplified version, because that's where the original pieces are coming from. If there was a context to this, if there's a real-world application, this square root would still cause some issues. So I need to look at this part, and because this only works where when x is 1 or greater, that's still going to be my domain for this simplified function. Even though this technically looks like all real should work, I need to go with the unsimplified version to figure out my domain. Okay, what if I did it, same function, same idea here, but now things are reversed. So this is g of f of x, different notation, but it kind of means it means g with the parentheses and then f with the parentheses, just like we had on the previous slide, just like we had here. It's just the f and the g would be switched around. So now I'm going to take x squared and I'm going to plug it into the x of function g. So just in reverse. So I would get this. Okay, plug x squared in for the x's I see there. This is something I am not allowed to simplify. I cannot rewrite this as the square root of x squared minus the square root of 1. I can't distribute that square root symbol, so I'm kind of stuck there. So I need to think of the domain of this version right here. So typically we'd say, yeah, probably every value will kind of work. If I put in a 3 in here and I square it, I would get 9 minus 1, which is 8. I can take square root of 8. But there is a little subset of numbers that won't work very well. If you think of fractions between -1 and 1, so right around 0, if I were to square, let's say 1/2 squared is 0.25. 0.25 minus 1 gets me a negative answer, and I can't take a square root of a negative value. So anything within that range from -1 to 1 is going to cause me issues, so I have to write my domain this way. I want you to note, I can plug in a -1 and a +1. That will give me a 0 in here, and I can take the square root of 0, but that gets a little bit complicated. You need to think through the domain ideas somewhat carefully. Okay, the last topic for this video, again with how we can make a new function or think about a new function from an old function, is the idea of an inverse. An inverse is basically found by taking an original function, reflecting it around or about the line y equals x, and you get your new graph. So if I were to take this parabola and reflect it around this line, I'd get the blue parabola. Another way of thinking about that is all the x comma y pairs switch, they flip-flop. So if on this parabola I had a point like 3 comma 9, maybe right around here, on the blue parabola it would be at 9 comma 3. Those things just flip-flop. The other thing I want you to note is that the blue parabola is not a function. It does not pass the vertical line test. So the way that we can look at the original function and know if the inverse would be a function as well is does this pass what we call the horizontal line test, because I can draw a horizontal line and it's going to hit the red graph twice. When I do that reflection, this will not pass the vertical line test. If that doesn't totally make sense, ask a question in class. Okay, inverse functions. The official definition is that if we have a function that is 1-to-1 and it has a certain domain and range, which they call capital D and capital R, then the inverse of that function, which we denote like this, f with a -1 there, that's going to have a domain of R and a range of D, so the domain and range just switch, and again, it's just kind of saying that the x and y values going from one to the other flip-flop. That's what this notation means here. This is what I want you to take away from this. What does it mean to be 1-to-1? It means that original function passes both the vertical line test, which means it is a function, and it passes the horizontal line test, which means its inverse will be a function. And then also that for the domain and range, they just flip-flop when you start talking about the inverse. So how can we actually find an inverse function? First of all, make sure that it is something that is 1-to-1, that it will pass both vertical line test and horizontal line test. Then go ahead and just take the equation, switch the x's and y's. So wherever you see an x, write a y. Wherever you see a y, write an x. And then take that new equation, solve for y, and you will actually find the inverse function. So let's look at one example here. Find the inverse to function f and state its domain if the original function f is the square root of x plus 3. So if you think of a square root function that has been shifted 3 to the left, that will pass the vertical line test. It also passes the horizontal line test, so that means the inverse will be a function. So how do we go about starting this process? You switch wherever I see an x here, I'm going to put a y. And this is kind of like y, so wherever I see a y here, I put an x, and then I just need to work backwards and solve for y. So first thing I'm going to do is square both sides. Okay, and then I need to subtract 3 from both sides. So this is my inverse function. And here's where I want you to think about things kind of carefully. This is a parabola, and we think of parabolas as having a domain of all reals. But I need to go back to the original, and I need to realize that this is a square root function, not a complete sideways parabola, but just part of that sideways parabola. And the range for this is going to be from 0 to infinity, right? It usually starts at 0, 0. This happened to shift 3 to the left. But it's only has y values from 0 to infinity. And as we flip-flop, as we do this reflection process, that range for this will become the domain of this. So here's a picture that kind of represents that. This is the square root function that we're thinking of. Its range is only 0 and above. So when I do that reflection over the line y equals x, the domain here will be 0 to infinity. Okay, so that's going to be my final answer there. And then you could also note that the domain of this was -3 and greater, and the range of the inverse was also -3 and greater. So this is the equation that we use, but we're actually only going to be looking at half of the parabola, not the full parabola. Okay, we're going to stop there. I'm going to let it play for a couple minutes, and there might be some questions I ask you at the end of this video.